In this section, we're going to talk about how the intermolecular forces in liquids affect the properties of liquids. The first property we're going to talk about is surface tension. To talk about surface tension, we have to talk about the molecules at the surface. Because those surface molecules have fewer neighbors, they're missing the top layer, they are less stable than those at the interior. They have a higher potential energy because they don't have that other layer of stabilizing interactions. So the surface tension of a liquid is defined as the energy required to increase the surface area by a given amount. So increasing the surface area is obviously going to have more molecules at the surface, and the higher the surface tension, the greater the intermolecular forces. So you can see here the surface tension of water is 72.8 millijoules per meter squared at room temperature. So if you spill water on a table, let's say, I'm sure have noticed that it tends to bead up. That's because it has a higher surface tension, whereas the surface tension of C6H6 has a much lower value of 28 millijoules per meter squared. So that's going to spread out more because it has less intermolecular forces present. So the factors affecting it, the stronger the intermolecular forces, the higher the surface tension will be. And if you raise the temperature of a liquid, it's going to reduce its surface tension. So that's going to increase the kinetic energy of the molecules, and that extra kinetic energy is defined as the increase in motion, and is going to make the surface easier to stretch. Our next property is viscosity. Viscosity is the resistance of a liquid to flow. It's measured in poise. And the larger the intermolecular attractions, the larger the viscosity. So you can see as we increase the number of carbons, we're going to increase the intermolecular forces. They're all London dispersion forces, but the larger molecules are going to be more attracted to each other. And you can see that as you move down the table, the viscosity goes up. Our next property is capillary action. Capillary action is the adhesive forces pull the surface liquid up the tube, and the cohesive forces pull the interior liquid with it. And so basically you're measuring the force going up versus the force of gravity coming down. The narrower the tube diameter, the higher the liquid will rise up the tube, and the greater the intermolecular forces, the higher the liquid will rise up the tube. An example of this is the meniscus. If you're looking at a liquid in a fairly thin tube, so like a graduated cylinder, aqueous liquids are attracted to the glass sides, and so they pull up at the edges, which is why we read to the bottom of the meniscus. And that's due to the competition between adhesive forces and cohesive forces. So it's attracted to the sides and then attracted to itself, so it pulls it up. So its adhesion to the water's adhesion to glass is stronger than its cohesion for itself. But something like mercury here is not attracted to the glass. In fact, it's a little bit, it's more attracted to itself, and so you get the convex meniscus there. The metallic bonds in mercury are stronger than intermolecular attractions, which is why you get that convex shape. Vaporization is our next property. Vaporization is how quickly something goes into the gas phase. So if higher energy molecules are at the surface, they might have enough energy to overcome the attractive forces. The larger the surface area, the faster the rate of vaporization. So here you can see some of these water molecules have enough energy to them to overcome the forces, intermolecular forces, and go into the vapor phase. Keep in mind that while we measure energy in a liquid with temperature, it's not only a small fraction of the molecules have enough energy to escape those intermolecular forces. If you increase the temperature, you're going to get more molecules with that escape energy. So the higher the temperature, the faster the rate of vaporization. To talk about vaporization, we should also talk about condensation. Condensation is the opposite, so it's liquid coming together to form, gas molecules coming together to form a liquid. In an open container, your vapor molecules are going to spread out faster, and so your rate of vaporization is going to be greater than the rate of condensation. But if you have a closed container where you can't spread out indefinitely, eventually you're going to come to an equilibrium where your rate of vaporization and condensation will be equal to each other. So now that we know about vaporization, a liquid with weak intermolecular forces is going to evaporate faster than one with strong intermolecular forces, just because there's less to overcome. More terms for you: liquids that can evaporate easily are said to be volatile. You can sometimes tell what's volatile by how much of an odor you're getting, because in order to smell something, it has to go into the gas phase. Liquids that don't evaporate easily are non-volatile. We can talk about the amount of energy needed to vaporize 1 mole of a liquid. It's the heat of vaporization, delta H vape. It is always endothermic. Remember, endothermic means it requires energy to be inputted. So delta H of vaporization is always positive. You always have to add energy to go from a liquid to a gas. It is also somewhat temperature dependent. And if you want to talk about the delta H of condensation, it's the opposite sign. It's going to be exothermic, but the same value. So the heat of vaporization, like we said, somewhat temperature dependent. So we have columns here for the delta H of vaporization at the boiling point and for at 25 degrees Celsius for a variety of common solutes or solvents. Okay, so how can we use this? Calculate the mass of water that can be vaporized with 155 kilojoules of heat at 100 degrees Celsius. So our delta H of vaporization at 100 degrees Celsius for water is, back to my table, 40.7 kilojoules per mole. So we know from our question we have 155 kilojoules of heat. We can set up dimensional analysis here. We know it takes 40.7 kilojoules of heat to vaporize 1 mole of water, and it's asking for mass. So we know that 1 mole of water is 18.02 grams. So then I can just do that math, and I get an answer of 68.6 grams of water. And there's it all worked out on a PowerPoint slide. One more practice: calculate the amount of heat needed to vaporize 90 grams of C3H7OH at its boiling point, where the delta H of vaporization is 39.9 kilojoules per mole. So here I would recommend pausing the video and working this through yourself, then coming back and listening to my explanation just to make sure that you understand the concept before checking the answer. So I would start with my 90.0 grams of C3H7OH. Then I can find my molar mass of that, which is 60 grams in 1 mole. And then I know that to vaporize 1 mole, I need 39.9 kilojoules. I can check that my units cancel. Grams cancels with grams, moles cancels with moles. I'm left in kilojoules, which is an amount of heat, so that makes sense. So I can calculate my answer, and I get an answer of 59.9 kilojoules. 59.8. Close. Probably depends there on, I didn't use enough significant figures in my molar mass. That's why it's a little bit higher. All right, dynamic equilibrium. So this is showing what we talked about a couple slides ago, that in a closed environment, if you put a liquid in there, at first the rate of vaporization is higher, but then as we get more molecules here in the gas phase, eventually our rates of forward reaction, so our rate of our rate of evaporation is equal to our rate of condensation. It doesn't mean that things stop evaporating and condensing. It means that the amount going into the vapor phase is equal to the amount going into the liquid phase, and so we don't see any net change, even though if you zoomed in, you would still see molecules changing phase. Our next term is vapor pressure, and that is defined as the pressure exerted by the vapor when it is in dynamic equilibrium with its liquid. We used this back in chapter 5 in Chem 103, using Dalton's law of partial pressures to account for water vapor when collecting gases by water displacement. The weaker the attractive forces, the more molecules you're going to be in the vapor phase, and so the weaker the attractive forces, the higher the vapor pressure, and the more volatile the liquid. Here we can see the effect of changing a container's volume, disturbing that dynamic equilibrium, but eventually we will get back to the same spot. So here initially our rates are the same. When you increase the volume, more are going to go into the vapor phase. When you decrease the volume, less is going to go into the vapor phase. Your rate of condensation is going to increase for a bit, but once you let it hit equilibrium, your vapor pressure is going to be the same in all 3 situations. Here's some vapor pressure curves. It's important to note here 760 millimeters of mercury is the atmospheric pressure, and where your vapor pressure curve hits the atmospheric pressure, it's your boiling point. So our red here is water. You can see the boiling point of water is there at 100 degrees Celsius, which is where your vapor pressure equals your atmospheric pressure. So for any of these, you can get the boiling point from this temperature versus vapor pressure curve. So let's practice which of the following is the most volatile if we look at this temperature versus vapor pressure curve. The most volatile is going to be the one with the lowest boiling point, the highest vapor pressure at any point, and so our answer is going to be this line here, which looks to me like ether. Which of the following has the strongest intermolecular attractions? So the stronger the intermolecular attractions, the lower the vapor pressure. The curve here with the lowest vapor pressure, highest boiling point, is this blue one, which is letter B there. Like I mentioned, the normal boiling point is the temperature at which the vapor pressure of the liquid is 1 atmosphere. And the lower the external pressure, the lower the boiling point. So if we vary our altitude, we're going to have lower pressure. So down here at sea level in Boston, water boils at 100 degrees Celsius. But if we go up to Denver, water's boiling at 94 degrees Celsius because our atmospheric pressure has dropped. That's why if you've ever made pasta, if you read the back of the box, there are different directions for if you're at higher altitudes, you have to boil your pasta longer in order to cook it because you're at a lower temperature. If you go all the way up to Mount Everest, your water boils there at 78 degrees Celsius, so much lower.